All right, welcome back everybody. So today I thought I would play a little bit with a autoencoder with deep learning, and I'm just going to use the MNIST dataset. And the reason why I am going to do this is because I have some ideas about how to use this with some spatial transcriptomic data moving forward. But I just want to make sure that the concept, the code that I am using works, because at work I have tried to do some of the auto-encoding stuff, and at least for the CosMx data that I have with like the kidney stuff, the auto-encoder wasn't converging very well, or the loss was still really high even after hundreds of epochs. So today what I want to do is I just want to make sure that the code that I'm using, and it's going to be essentially the same as here, just replacing the gene expression data with the labels, and we're not using labels because it's an autoencoder, but replacing the gene expression data with pixel data, and it's 8-bit, so 0 to 255. So if you guys are interested, feel free to comment down below. Maybe you have some ideas about how we could use an autoencoder with some of the spatial transcriptomic data or other bioinformatics type data as well. And it's a way to just embed the high dimension data into something that's a lot smaller. So today we're going to embed the MNIST from 784, so 784 pixels, 28 by 28, into a 16 number vector, a 16 element vector, and we're going to be able to rebuild the image with those 16 values, which is really cool. So yeah, if you guys have any recommendations or ideas about how we could use this in our bioinformatics data, feel free to leave them down below. Let me know and we can potentially play with it. But make sure that you're subscribed. That way the next video that comes out, you guys are like right on top of it and able to join along for the ride. So let's jump right into our Conda environment, or into our terminal to build our Conda environment. So here we can see that I have the Anaconda prompt. So this is basically just the base environment. And what I'm going to do right off the bat is I'm going to create a Conda environment. And if we remember back from the CUDA video that I had made of creating a Conda environment that we can put all of our CUDA tools inside of and keep them contained, we need to specify the environment as Python 3.8, because we know that that one works for installing all of our CUDA toolkits, Pytorch, all of that type of stuff. So if we go ahead and do conda create, and then -n for a name, we can call this one autoencoder, and then MNIST. We'll call it autoencoder MNIST. And then we have to specify Python equals 3.8. So let's go ahead and spin this up. Hopefully it's pretty quick. And then we'll go ahead and also install all of the packages that we need in order to use CUDA inside of our Conda environment. So if you guys have already watched the video, let me go ahead and get this going here. Already watched the CUDA video, feel free to skip ahead into the actual Python, well, just after the CUDA install, because there's a couple other packages that we're going to need in order to use Pytorch. So let's go ahead and get into our CUDA environment and make sure that I'm doing everything that I need to here. So yeah, I'm just going to copy and paste from the GitHub page, and if we remember, I'll just pull it over here. So here's the GitHub page for the CUDA video that I had created. Let's kind of go over some of this here quick. We'll get this actually running. Copy, and then back over to this guy. What's it not happy with? So I need to activate it. We don't want CUDA test. We want to just install. So pull this back over. It's not going to let me know. Copy and paste. Perfect. So now it's going to go through and it's going to install those 3 lines. But so the things that we're going to use today, I really like Spider as an IDE for Python because you can pull your script up on one side. You have a terminal, and then you also have an area where you can see your plots and all of the environment variables. So it's a lot like RStudio in that aspect. It's just much more friendly for Python than RStudio is, or at least in my opinion. The data set that we're going to use, like I had mentioned, is going to be this MNIST data set. And you can go and find a lot of pre-made data loaders and these objects, but because we're going to be using the same or similar code to something that is in a CSV format, or that we can export as a CSV format, like our gene expression data and our labels or cell phenotypes, I really think that this, at least this data set here, where you can download the CSV and the train and the test, and we'll just combine it later on, but is something that's very useful. So if you really want to follow along, feel free to download this GitHub repository. And once it's downloaded, let me see if I can pull this up. This one here, it'll come in this archive folder, and then we have to extract it in order to get this train and this test. So they're kind of big, but Python will be able to handle it just fine. And then, like I said, we're going to concatenate it together, and then we'll pull out the response variable. So that's going to be what number the MNIST is. So for example, if we scroll down here, we can see that all the pixels in this row are corresponding to a number of 7. So if we rebuild that picture, it's going to show a number 7. And then all of the predictors. So the code that I'm going to kind of follow, aside from the data loader, is this here. I'm going to create my own data loader instead of using a pre-made one, because I think it's very important that we do start off with this tabular data if we want to later on go and implement some of our own, instead of using this pre-built stuff. And there's actually 2 of them open here. So, but anyway, I'll put those in the comments down below. But after we get our Pytorch installed, we're going to go ahead and make sure that our CUDA works. If I can find it again, it's still going. We're going to make sure that our CUDA works, and then we're also going to install a few Python packages along with Spider. So here we can do conda install-c anaconda. So the channel that Spider is in is anaconda, and then we can go Spider, and then we can just specify Y. So it's going to go through, solve the environment, and install Spider without us having to specify that we do want to install it. Hopefully it's pretty quick. And then 2 of the packages that are for Python that we want to use that we don't have installed in just a basic conda environment is going to be 1. We need pandas. So we're going to use pandas to read in our CSV files and then pull them together. And then the other one is matplotlib. And what matplotlib is going to do is it's going to allow us to visualize 3 different things. One is going to be the image that the MNIST data has, so like the original data. The second is going to be our reconstructed image. So after it goes through the choke point, or the lower dimension of the autoencoder and then gets rebuilt up or decoded back into the original image, we're going to be able to we're going to be able to visualize that. And then the third thing is we're going to be able to see our loss over time or over our iterations. And that's going to allow us to see if we have something that is wrong. If our loss function is just going to be straight across, we're not actually going to see it decay, and we really want to see it decay. Awesome. So now we have that installed. Let's go ahead and do pip install and then pandas, and then I wonder if we can do matplotlib right off the bat and then specify yes. It did not like that. So let's do one at a time. Pip install pandas. It's not going to like that either. Is there anything else that I am missing? I don't think so. Pip install matplotlib. Plotlib. So Spider is installed. Okay. So we're going to go into the folder where I have those files at. That way our data is readily available when we launch Spider, and it's going to be right in our working directory. So we're going to go D. So we're in here, and then we can go, what was the folder called again? Just Auto-Encoder. Well, that's pretty handy, huh? CD Auto-Encoder. Encoder. Awesome. So in order to start Spider from the terminal, it's super easy. All we have to do is type in Spider. And then it's going to go ahead and launch it up, probably on my other monitor. So let's discard. Nice. All right. So this has an old temporary file in here. What we're going to do is we're going to go D and then Auto-Encoder. Perfect. Now let me all right. So we have import torch, we have import pandas, and we're going to import pandas as PD. Let's go ahead and we'll not save it. It should work. And then we want to import NumPy. So from pandas, we're going to get a data frame object, and then we have to convert that data frame object into a matrix or like a list of lists, as NumPy does it, an array. And then we can go ahead and convert it from the NumPy into a tensor, which Pytorch uses. So we'll import NumPy as NP, and then we also want to import that matplotlib.pyplot as PLT. So that's going to allow us later to do all of our plotting, which will be really handy. So let's go ahead, copy all of this and get them choochin'. And then let's go ahead and import some other things that we're going to need. So we're going to need from torch.utils data, and then we want to import the data set, because when we create our, we have to do two different things when we're working with our input data. Oh, here we go. And then data loader. We have to create a data set. And what that is going to do, there's a couple features that are required in a data set for the data loader, which is the next thing. And one of them is we have to be able to specify within the class, we need to be able to specify the length function. So what is the length of the data set? And then we'll have to have a way to get the particular data that we want out of the data set as well. And then the data loader will convert that into something that we can use when we are training our model. So we got those guys. Now let's read in our MNIST data. So we can do MNIST test equals pd.read CSV, and then MNIST test.csv, and then we're going to copy and paste this into train, and let's see if this works. Cool. And then we can go back to our variables, and we can, of course, see our two different variables. Since we're going to create an autoencoder, what we can do is we can concatenate these together. We just want to use all of the data and make sure that we have as much information as possible to train our model to come down to that choke point or the latent space, the restricted area, and then build it back up. The more data we have, as with all things, the better. And since we're not using this necessarily for predictions right now, it doesn't make any difference if we use some of the data or all of the data. So we're going to go ahead and use as much of the data, all the data as possible. So we can do MNIST data equals pd.concat, and then in here we can specify what we want to concatenate. So we want to put together our test data and our MNIST train data, and then run that guy. So now we can see we have 70,000 images and 785, 84, one label, and then all of the pixels that correspond to the pixels, or all of the columns that correspond to the pixels. Cool. And then let's just clean this up here. So we can delete our MNIST test, and we can delete our MNIST train, just to keep everything as clean as possible. Okay. Get my screens organized here. All right. Back in action, as they say. Since we are using a CUDA environment, what we can do is we can, in the code here, we know that CUDA works for us, but it's generally good practice to do something like identifying the device that's available. That way, if you want to run this inside of a Conda environment that doesn't have all of the CUDA toolkit stuff installed, or the Pytorch version is the CPU version, what this will do is it'll automatically find out whether or not you have CUDA available, a GPU available, and if not, it'll just default right to the CPU, and then you don't have to worry about changing the code later on too. So we'll do equals torch.device, and we're going to want to look for in torch device CUDA. If torch.CUDA is available, so this is the code that we always look or always use to make sure that CUDA is installed correctly. So if we go down here, we should get true. There we go, true. So we will get CUDA if we do have it available. Otherwise, else we're going to have to default to the CPU, which is fine. This is kind of a small data set. It will probably take a long time. I have not run on the CPU, so I'm not 100% sure how long it will take, but it's there if we need it. All right, so then we're going to do two things next. We're going to split our MNIST data into the predictors, or the features that we're going to actually build the autoencoder with. And then since we're using a Pytorch data loader, we can do this on our own too. We don't have to use a data loader. But since we are using the data loader, what we have to do is also specify the response variable, which is going to be this first column here, the label. So in order to extract out everything that is going to be our feature set, for example, what we can do is do MNIST data. And then what we want to do is we want to drop a particular column. Columns equals, and then that column label or name is label. So if we could do label, let's go ahead and run that to make sure the code works. Perfect. So now we can see 784, all the features. And then Y, what we want to do is do MNIST data and then dot label. So the column name that we want is label. If we do that, boom, now we have a single columned pandas series. Perfect. So let's do separating data. Cool. Now what we can do is convert these. So we'll have to do two different things with the actual feature set. We're going to have to convert it to a NumPy array, and that's easy enough. But we're also going to have to make sure that our features are between 0 and 1. Let's just go ahead and start this. I'll show some code to make sure that the NumPy array actually is between 0 and 1. So we can do x equals np stack. And then what we want to do is get the values for n, c in our items. Cool. And then the axis doesn't really matter here, or potentially does. So rows, what we want it to do is rows. Every single row is an image, so we want to keep all of that in the same array for NumPy. And then as type, we're just going to specify this as a float, because later on what we're going to have to do is convert this into decimals. Right now they're just integers, but we're going to need to convert them to float values. So now if we look at the minimum values that are inside of our NumPy array now, we can see the minimum is 0. So that would be like a black pixel. If we do maximum, what this is going to show us is 255. So this is like a full white pixel, and then you have grayscale in between. But to make sure that all of the pixels in our image have the same weight and they pull everything the same, what we're going to do is we're just going to divide all of our features by 255 to get a scale from 0, because it's our minimum already, to 1. So the 255 that we see here will just be 1 afterwards. So we can do x equals x divided by 255. So let's run that, and then let's just check here to make sure that it did scale correctly. And there we go. So now we have a float from 0 to 1. So 0 doesn't change when doing that. And then let's go ahead. So this is going to be features. And then down here, let's do our response, just because with the data loader, we're going to need it. Data loader, we're going to need it. So y equals dot to NumPy from the pandas. And there we go. So now we have y. It's an array. We can see, we just type in y here. It's like in R, how we would see a vector between the brackets here. And we can see that it's an integer. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool. All right. So like I had said, in order to use Pytorch here, we're going to have to do 2 different things. And the first one is that data set class that we need. So if we do class MNIST dataset, this has to take in this data set. I'm actually going to have to come up here and do data loader too. Data loader. It's a class, and then we'll run that. Great. So then we can do data set, and then inside here, we'll have to do an init, like all of the Python classes, and then we'll have to do 2 functions after that to report the length of our data set, and then allow us to extract an object, well, not an object, an item from it if we were to specify an index. So initially, let's do setup object. So we'll do def and then init, and we're going to specify the self. And then when we are creating our data set, we're going to pass in our x and we're going to pass in our y. So we're going to get our features, and then we're going to get our response, for example. Okay, and then we can do self dot, I don't know, x lowercase is going to equal our features, and then Pytorch, like I had said at the beginning, is going to require the elements to be in a tensor, which is just a fancier array from NumPy that we can see here. So what we actually need to do is do torch dot from NumPy, and then specify what we're going to actually put into our self.x, which is going to be our features here. And then we can do the same thing for y, and since we have both of these as NumPy arrays, we can go ahead and do just the same thing from NumPy and then response variable, which is really easy. The other things that we have to do, len function, and that's going to take just in our object something, and then let's do def get item, and then we have to do our self, and then we have to do some index that gets passed in, right? IDX, we'll call it. Cool. And then something else. We come back up here. This is just really easy since we have the self y already. We can just grab the length of our response variable. Since it's already one dimension, it's not going to take anything too complicated. So we can do return, and then I keep doing that from R. We can do the length of our self object and then our response variable. So that'll just give us inside the data loader, it'll give us the number of elements that are inside of our data sets. Okay, and then down here, so let's get rid of this guy. Let's put some code, setup object in here. And then define length function. And then if we come back down here, we're going to define getting the item. And then come back over here and add in our dunder as they were. Okay. So in here, we need to grab out index of both the X, our features, and the index of our response. And it's pretty easy. So if we do feature index, we can go something like self.x and then index, since they're just NumPy arrays, and then response I, index of self.y index, and then we'll return these. So return feature I and responsive I. So later on, when we don't need the response, we can just do something, a variable, comma, underscore, and then we can just throw away that response since we don't actually need it. Cool. Yeah, that didn't do anything that we need. Okay, so we can go ahead and run that. Perfect. Now we can actually pass in and create our data set from our MNIST data. So we can do MNIST data set is going to equal our class MNIST data set. And then we have to pass in, like I said, our features, which is X, and our response, which is Y. And then let's go ahead and run that. So now we have our MNIST data set, which is cool. Create data set. Now we have to create our data loader and just use our data loader. Create a data loader. In order to do this, we can do MNIST data loader equals data loader because we imported it up here. So we're going to pass in our data set. So data set is going to equal our MNIST data set. And then we can specify a few other things. So the batch size, I've used up to 512 and it seemed to work just fine. So I'm going to go with that again because I'm going to run a bunch of epochs and it seems to work faster with more images in a single iteration. So we can do batch size equals 512. And this is just a 3080 10 gigabyte. So if you're running it on something like a cluster where they have like an A30 or some actual GPU that's built for its CUDA resources, feel free to do with that as much as you would like. And then for each one of our iterations, we're going to go ahead and turn shuffle on, so true. Then we can go ahead and make sure that that runs. It does not shuffler. Am I spelling it incorrectly? I have to be. Oh, shuffle, not I did spell it wrong though. There you go. So now we have our data loader. Here we go. Perfect. So we can see that 70,000 divided by that 137 different batches or elements that we have. Each one has, on average, 511 images. So we're pretty darn close. All right. So now we get into the fun stuff. So now we can actually start defining the model architecture. Let's go ahead and add some space here so we don't strain ourselves looking at the bottom. So the class, we're going to build a new model class, and we're going to call it Auto-Encoder. Sounds easy enough, doesn't it? And then what we're going to do with this is we're going to pass in torch, NN, and then module. So we have to have two different elements to our autoencoder, right? So the first part is going to be the shrinking down. So if we go back to this guy and then look here, where is it at? So the first part is going to be this restriction part. So we have our 584 different pixels here across the top. And then we're going to compress it and compress it and compress it down. And from this wide to the narrow part is called our encoder. So we're going to encode some latent space with our pixels. After our encoding with that latent space, what we can do is then pass it back into this expansion part here. And what that expansion part is called is a decoder. So we'll have 16 values that represent our entire image. And so we're going to pass our 16 values into our decoder, and we're going to get 784 pixels back out, which is really, really cool. So let's go back to our spider. So we have to do, like I had said, two different parts. We have to do our encoder. So we have to initialize our model, def init, and then we'll pass in just our model. Specify super init. All right, so now we can actually start building the model. Oh, my back. So this first part is going to be called our encoder, and it's going to equal torch.nn and then sequential. So we're going to do each one of these steps one after the other until we get down to our latent space. Let's go ahead and do that. Cool. So we need to first start off, since we have vector data already, what we can do is just do linear, and then our input features is going to be our pixel dimension, so 784. And then our out features can be really anything that we want, as long as the output of this is the input of the next one, right? So it's generally okay to do a few different, let's go back to that picture, a few different layers here. The more layers, I have read, the more layers that you start putting into this, the harder it can be to do back propagation, because it just gets overly complicated. But we're going to do just the same number as here. So we're going to do 784. We're going to compress that down to 128. And then 128, we're going to go down to 64. And then from 64, we're going to go down to 16. Maybe we'll do one more from this. 64, 32, then 16. Just so it's a little bit more gradual and it's not so drastic, if you will. So the output features here, we'll do 128. And then we'll do a comma. And then what we're going to do is copy it, because simplicity. And then we'll do 128 to 64, 64 to 32, 32 to 16. Yeah, that should work. 128, 64, 32 to 16. 16, 32, and 64. We can see that our input features are the output of the previous layer, right? So you have to make sure that that matches. Otherwise, the model gets all angry, because if you're trying to feed 129 numbers into 128 inputs, it doesn't work. So something that's really common too between here is something that is called linear rectify linear. So what that does is basically anything that's less than 0, it floors to 0. Anything greater than 0 can keep that. I have read that something that works a little bit better than just the straight ReLU is leaky ReLU. So you'll actually have a slight negative slope for that. But if we do torch.nn, a lot of times they'll do .ReLU there. But what we're going to do today is actually leaky ReLU. And then inside here, the variables, negative slope, there we go. We'll do negative 0.1. This is the default, so even if you don't specify anything, it's going to default to this. But I have read that the leaky ReLU performs a little bit better than just straight up rectified linear. So if we go ahead and do those, this is going to be our encoder. So if we pass in one image here, and assuming the model is trained, we pass in one image, 784 numbers. What we're going to get out is a latent space with 16 values. So you can think of this like principal component analysis, where we can have a ton of genes, right? And then a lot of that variation is going to be, because of the principle of principal component, is going to be in the first, second, third, and decaying, so on and so forth for principal component analysis. Here, the 16 numbers are going to encode for all 784 pixels. So that's our coder, our encoder, build the, let's call it encoder. And then with the decoder, we're just going to essentially undo what we had done for our decoder. Uh-oh, puppy. Build the decoder. Are you Dally? Hey. Let's see if she talks to me. So we'll do self.decoder. It's going to equal torch.nn.sequential. And then start filling this in. So the input here is going to be the output of our encoder value, or encoder element. So we need to start with 16 and then output 32 and then go back and forth that way. So let's go ahead and copy this. We'll put that here. 16, 32, and then we're going to copy this for 3 times. 1, 2, 3. Something's not right. Ellie, what are you doing? Hey, what's up, baby? So now we got 32 as our input and 64 as our output. We'll have 128 as our output and then 784 as our output. 128, 64, and 32. And then we can go ahead and do our leaky ReLU in here. And then the final here, so we can imagine that our linear layers don't have any bounds on them, right? So what we need to do is we need to tell the decoder that the output values we want are between 0 and 1. And the function that Pytorch has in order to do that is just a sigmoid function, right? So you can do torch.nn.sigmoid. Make sure I spell it correctly. Sigmoid. And that tells the decoder that the final layer, the last thing you want to do is make sure everything is scaled between 0 and 1. That way when we're comparing it to our input image, which we have scaled above to be between 0 and 1, everything lines up correctly. We're going to try to match the exact same values on our output. Then what we need to do is we actually need to tell our model how we want to use these layers inside. So right now, it doesn't know that we want to use our encoder first and our decoder. It just has these as elements of our model. So we have to tell our model how to use encoder and decoder. Encoder and decoder. And what we're going to do is we're going to take in... So we'll specify forward. We have to take in our object, so our model, and then some image value. We'll just call that X here, but it doesn't necessarily relate to the element above. It's what we're passing into our model. And we're going to have encoded. Encoded is going to equal self.encoder and then that value, which is pretty easy, right? So we're going to take our input data, which is going to be a part of our data loader, but it's going to be essentially a row of our pixel values. We're going to pass it into our encoder, and we're going to get out 16 values that are now our encoded image. And then we have to decode that back, and then later on we'll be able to compare that to the original image. So decoded is going to be self.decoded or decoder, and we're going to take in to our decoder our encoded values. Encoded. Pretty easy again, right? And then all we have to do is return our decoded, because that's what we're going to compare to our original image to make sure that the model is doing what we want the model to do, encoding accurately our image. Cool. So now we have our model specified. Let's go ahead and actually pull this in. There we go. So now we have a class of autoencoder, and we can specify model equals our autoencoder. And there we go. What happens if we do print model? It would help if I spelled it correctly, though, eh? Model. I wonder why it's not showing everything here. That's fine. Print model. And there we go. We can see everything that we have specified here is now part of our model. Something, since we do have CUDA, that we need to keep in mind is that by default, everything is not sent to the GPU. We have to tell Pytorch that we want to send our model and our data later on to our GPU to use our GPU's CUDA cores to do all the calculations and then do everything there, essentially. But by default, let's see if our model has a device yet. Model get device. Autoencoder object has no attribute. Okay, well, what we're going to do anyway is we're going to send it to our GPU. So model equals model dot to and then device. So remember, our device is our GPU. CUDA. Device. Let's see if it works. Sending it to the GPU. Chugga chugga chugga. I did see memory increase a little bit. Cool. So it does look like it worked. Now let's see if our get device. Why does that not work? Autoencoder model. It should, but that's fine. Well, we'll skip over it. It went to the GPU and we don't have any errors. That's all that matters, right? All right. So now we have to set up a couple other things to use when we start training our model. And the first thing is going to be our loss function. And then the second thing is going to be our optimizer. How does the model know how to get better? So the loss function that we can use to assess whether or not the model is improving, we're going to do torch.nn and then MSE loss. I did read that the cross entropy loss works as well, but when I was training, initially I was trying it, the cross entropy loss didn't seem to be improving drastically as time went on. So we can do our specify our loss function. And then a lot of times with the optimizer, they will specify the atom model. So if you do torch.optim, the atom, there you go. Params we don't need. Oh yeah, we do some model parameters. We have to take the parameters from a model to know how to improve. The learning rate. Watched another video yesterday and they used 3E-4 because apparently Andrei Karpathy from Tesla way back had used that and thought that was the greatest. And then weight decay, I don't know if this is all that beneficial, but this is what the example had, so we're going to go ahead and use it here. Turn that off. Let's make sure. Oh yeah, I do optimizer. Optimizer. Why is it not happy? Oh, S parameters. Let's try that. Hopefully, we get less errors. Woo! All right, cool. So now, set up the training loops. I don't know if TensorFlow uses the exact same thing. For some reason, I feel like way back in the day, they had a way to do all of the training that was more wrapped than Pytorch, but I like the customization that Pytorch allows us to do. But so in order to keep track of everything, we're going to specify a losses variable that we're going to store the loss that we calculate after each encode and decode comparing to the original image, and then an output will allow us to hold all of the values and stuff that we had. Further, let's specify how many epochs, or how many times to loop through all of the data, and we'll do epochs equals, let's just do 10. We'll test 10. And then what we can do is now do our loops. All right, so for epoch in the epochs that we have, so we'll have to do range of our epochs. Let me scroll back up here. We're going to go through our data loader for each of our epochs. So we can imagine our epochs are 1 through 10, and our data loader is 1 through 137. So we'll have to do then for, and then image underscore. Remember, instead of our data loader, we have our response variable, but we don't need a response variable for an autoencoder because we're not training it to predict the response. We're just training it in order to learn the latent space in order to maintain as much information about our model as possible. In our data loader, in our MNIST data loader, okay, then we'll get our image, and we have to send, because remember our model is on our GPU, we have to send our image to our GPU as well. So image.to device, or to our CPU. Okay, and then we'll pass our image into our model, and remember that our model has the full forward, so it's going to get both encoded and then decoded back. So what's actually put back is going to be what we call our reconstructed image, and that's going to be our model, and then the image that we pass in, or an image here is like a batch. So we have 512 images in our image variable there. Great. And then we can calculate the loss. So the loss function that we have, we're going to pass in our reconstructed image function, reconstructed. And then what we want to compare reconstructed to is our original image. And that's going to tell us how different these two are in order to go back and update our model, like fix it a little bit. And then we have to do optimizer and then .0 gradient, because we don't want to change our model now. So we have to specify zero gradient. That way when we actually update things with our loss, we're not changing anything. We don't need any of this. Okay, so with our model now set to just update instead of zero gradient, yeah, it's just update. We can do loss, and then we can do a back propagation, backward. And then we'll step our optimizer forward again. Optimizer dot step. Okay. And then what we want to do is save our loss that we have calculated here for this particular iteration. That way we can track it over all of the data sets that we have, or all of the elements of our data set, and then across our epochs as well. So we'll append our losses. So losses equals losses dot append, and then loss. If you look at loss, it's not just a bare number. It's a number, and then it's got a class of like loss function or something like that. MSE. It's got this as a sort of class. So we just want to take the number out of it. In order to do that, we'll just do item, and what that does is it spits back out the number, because that's all we really care about. And then what we can do is just go on. Let's do printing of we'll print some information after each one of our epochs. So epoch, this will be our first number. Keep doing that. And then tab, and then we'll do, then we'll just do loss specified, and then 1. And then we can do dot format, and then in here we'll do epoch as the first thing that we're going to pass through. So epoch, and then loss here we'll do losses. Let's do losses, and then we'll do the last number for that. So we'll just take the last loss after all of the iterations in our data loader is done. Let's round it though, because it's a float. Round losses, and then in here we'll do 3 decimal places. That should work. Okay, I don't think there's anything else. In the tutorial, they have this outputs.append. I think it's this epochs image reconstructed. But in reality, it's a for loop, so nothing's really hidden. When we go on to later, we'll just be able to use image and reconstruct it from the last iteration of our data loader. Output. Should we see if it works? So we'll go ahead and see if we start getting values. There we go. And it looks like it's decreasing. While that's running, let's go ahead and prep some of the plotting stuff that we want to do. You can see I got all that good. All right. So some of the plotting stuff. So we'll do our input image. Input image is going to be our image. So now that it was the last iteration of our for loop, we're going to have image. And our image is actually, let's see if this works. Image.get device function. Yeah, it's still on our GPU. So we have to pass it back to our CPU if we're going to do some plotting. And then we need to reshape it, because then we have 512 sets of 784 numbers. So we'll do input image equals the input image, and then we'll reshape it. we'll get this back to 28, 28. So let's go and do that guy, and then we can do pyplot dot imshow of our input image. And we have to remember that our input image has 512, right? So we're not able to pass everything through. Input image 368. I wonder why that is. 512. That's fine. But we still have to specify. Let's just specify the first one for the sake of cleanliness. So if we go ahead and do that, head back over to plots. So this is a real image that was passed into our model. Let's look at the second one because that looks really bad. 0 index is fun. 4, that doesn't look too bad. Okay, let's clear this guy. So we have a 4 as our input image. What does our output image look like? So we'll do output image equals reconstructed. Remember, reconstructed is after it's being after it is rebuilt again, and then we need to pass it back to our CPU, and then for some reason it has some element of like back propagation. So what we have to do is we have to detach, and then numpy, create a numpy array again. Okay, so then output image, we have to reshape this guy too, equals output image, just like with the input image, dot reshape, -1, 28, 28. Let's see if it works. Brilliant. And then we can do pyplot imshow our output image. And then since we specified the second element with index of 1, we can do that here. Does not look very happy though, does it? Let's see if we can bump this up as we keep coding. 25. We'll do 25 epochs. And then we'll get the plot function ready in order to do the loss over time, loss over iterations. In order to do that, what we can do is just plt.plot and then losses. Since we already have losses as our single numbered vector, or like a vector of one dimension, this should have take in a single number and plot it out. So let's clear this and see if this had worked. And since we had shuffle, it's not going to be the same number. Okay, so we got a 9 as our input. Let's see if our output looks like a 9. That's not bad. Let's see, what if we change this? 2. That is a terrible input number. 3. That is a terrible number too. People have terrible handwriting, don't they? That's a 2. All right, so let's start there. Clear that one. So we'll do 4. So it's a 2. What does this guy look like? That's not bad. If we let it train a little bit longer, it would probably look much better. So let's see if we can just do 25 more epochs. Perhaps the loss will continue to decrease. 0, 2, 4, 2, 5, 2, 3. So it looks like it's still training a little bit, or still learning and updating. And something with an autoencoder too is that the longer that we let it run, within reason, of course, right? The better it's going to start fitting our data, which we want, because we want our output, or we want our latent space to fit our input data like perfectly. That would be a perfect world. There's no loss of information by shrinking these 784 numbers down to only 16 numbers. So that would be absolutely peachy if there was no loss at all. Got back to our horrible handwriting. Let's start back at 0. This microphone's in the way though, eh? That's a terrible 2. 0, 1. 2. That That looks like an 8. We'll go with that one. All right. 2. This 4 will replace. Wonder why that happened. 4 will replace with a 2. And then we'll plot this one. This is after 50 epochs. That's pretty good. We plot our losses. We can see it's actually still decreasing. So we could probably keep running this longer and longer. But to show and kind of wrap this up, it looks like we are able to, the code works in order to do auto-encoding. We have an encoding function, we have a decoding function, and I'll show that here quickly before the video ends. And we're able to rebuild, with more training, our original data from this latent space of 16 numbers. So wrapping up this latent space of 16 numbers, if we do model dot encode, so we want to encode this 8, for example, into that 16 number latent space. Encode, so this is part of our object here. Encoder, we'll do input image and then number 2. So we run this guy. Need to put it in parentheses though, otherwise that's not going to work. Okay. Oh no. Image is not on our GPU, which is fine. We'll just do image instead. There we go. So there are the 16 numbers here on the bottom that allow us, through our model, to rebuild this 8 here. That's all we need are these 16 numbers, and this is the output that we get. And these 16 numbers were built or computed from this image. That's really cool. So make sure you stay tuned if there's anybody still watching for future videos, because I am hoping to really apply this to some of our spatial transcriptomics data and see whether or not we're able to get some really cool deep learning applications with the Auto-Encoder. So thank you for watching if you're still around. See ya.